All right, let's get right into it. If you're a reliability professional, or really anyone in mechanical engineering, you know some parts are just more critical than others. Today, we're zeroing in on what's arguably the heart of almost every single rotating machine out there, the rolling element bearing. You know, understanding this thing isn't just a nice to have, it's absolutely fundamental if you want to prevent catastrophic downtime. So let's dive in. So the textbook definition is pretty straightforward, right? It provides positioning and rotational freedom while transmitting a load. But what does that really mean in the real world? Well, a bearing's number one job is to conquer friction. It's this incredible little device that transforms the high resistance of two things sliding against each other into the super efficient motion of rolling. And that simple principle, it's the bedrock of all modern industry. But as we're about to see, the engineering it takes to make that simple principle reliable, well, that's anything but simple.
So what happens when it all goes wrong? When a bearing fails, the machine stops. It's that simple. And when the machine stops, production stops. We're talking about costly, unplanned downtime, lost product, and a massive headache for everyone involved. So you can see, understanding this component isn't just some academic exercise, it is directly tied to protecting the bottom line.
To stop those failures before they even start, we have to go back to the beginning. I mean, really understanding the fundamentals of how a bearing is built and how it's supposed to work is the absolute first step on that journey to true machine reliability. Okay, so every rolling bearing basically boils down to four main parts. You've got your inner and outer rings. These are the hardened, super precisely ground tracks, or raceways. Then you have the rolling elements themselves, either balls or rollers, and their job is to carry the load between those raceways. And finally, you have the cage, or retainer. This part is critical. It keeps the rolling elements perfectly spaced out to manage friction, heat, and all the dynamic forces. And you gotta remember, every single one of these parts is a potential point of failure. So this brings us to the fundamental trade-off in bearing design. It's the classic showdown, ball bearings versus roller bearings. Ball bearings with their little spherical elements make what is essentially a point of contact with the raceway. This makes them great for high speeds and lighter loads. But roller bearings, on the other hand, use cylinders or tapered rollers, which creates a line of contact. This spreads the load out over a much larger area. And what does that mean? It means a much higher load capacity for a bearing of the same size. This one geometric difference is why we have these two major families of bearings. Okay. So if we know how they're built, can we predict how long they're actually going to last? Well, this is where engineering gets a little bit into statistics. Bearing life calculation is the tool we use to try and answer that all-important question. Now, anyone who's ever had to select a bearing has seen this term L10 Life. Let's be crystal clear about what this is and, more importantly, what it isn't. It's a statistical calculation, okay? It's defined by ISO standards, and it represents the point where 10% of a huge group of identical bearings running under perfect lab conditions are expected to have failed, and this is the key from subsurface material fatigue. It is a design benchmark, not a guarantee of how long it will last in your machine. And this is the magic formula, the ISO 281 equation for L10 Life. C is the basic dynamic load rating. That's a number you pull from the manufacturer's catalog that represents the bearing's built-in capacity. P is the equivalent dynamic load. That's the real combined radial and axial load your bearing is actually seeing in the application. And that little exponent P is 3 for ball bearings and 10/3 for rollers, which reflects that whole point versus line contact difference. Now remember, this entire calculation assumes everything is perfect. Perfect alignment, perfect lubrication, and perfect cleanliness. And that brings us to what might be the most critical takeaway for any reliability pro out there. The calculated L10 life, that's a laboratory number. The actual service life is what happens in your plant, on your machine. The gap between those two numbers is where reliability is either won or lost. Things like contamination, misalignment, lubrication breaking down, improper installation. These are the real-world assassins that kill bearings, almost always, long before they ever get a chance to reach their theoretical fatigue limit. So this brings us to the most important part of this whole discussion. Let's just forget the textbook theory for a minute. Let's look at what people like us actually see on the plant floor. Let's investigate the real reasons bearings fail. So let's start with the classic textbook failure, subsurface fatigue. It all begins with a tiny crack under the surface of the raceway. Eventually, that crack works its way to the surface and a little piece of material flakes off. We call that a spall. Now, as you can see in these pictures,
That first spall creates a stress riser, and with every single pass of a rolling element over that spot, the damage just grows and grows exponentially until you have a catastrophic failure. But, and I have to stress this, out in the field, this is the exception, not the rule.
And you don't have to take my word for it. This quote from the SKF General Catalog. Honestly, every engineer should have this memorized. Field failures are not generally caused by fatigue. They're caused by everything else. Bad lubrication, dirt getting in, poor installation. This right here is the key insight. We have to stop looking at the bearing's load rating and start looking for the real root causes of failure. And these root causes really fall into two big buckets. First, you've got pre-operational damage. This is stuff that happens before the machine even runs for the first time. Things like using the wrong shaft fits or damaging the bearing while you're mounting it. Then you've got operational damage, which is everything that happens while it's in service. This is where ineffective lubrication, dirt and water getting in, and failed seals just do their destructive work day in and day out. So if we know that these real-world problems are the true killers of our bearings, how do we fight back? Well, the answer is to stop waiting for things to fail and start listening to what the machine is trying to tell us. We have to be proactive. We need to read the warning signs through condition monitoring.
So how do we listen? Well, we use condition monitoring to track the vital signs of our equipment. Oil analysis is great. It can spot tiny wear particles and contamination. Thermography can spot overheating before it becomes a big problem. But really, the gold standard for checking bearing health is vibration analysis. It's basically like giving your machine an EKG. It's capable of detecting these minuscule defects long before they become catastrophic failures.
Oh, this is fantastic. This shows you exactly what I'm talking about. The bottom graph there, that's the vibration signature of a perfectly healthy bearing. It's low, pretty flat, it's just background noise. Now look at the top graph. See those distinct spikes? Every single time a rolling element passes over a microscopic pit on the raceway, it creates a tiny impact, a shock wave that our sensors can pick up. This technology literally makes the invisible visible. It's undeniable proof that a problem is developing, long before you could ever hear it or feel it with your hand. So all of this, understanding how things fail, using condition monitoring to see it coming, it all builds into a much larger strategy. It's really about a fundamental shift in your mindset. It's about moving away from that reactive, fix-it-when-it-breaks culture to a truly proactive, reliability-centered way of thinking.
And you know what? The data makes the business case for us. Just look at this chart. A purely reactive, run-to-failure strategy is incredibly inefficient. Now, time-based PMs, that's an improvement, but you still run the risk of replacing perfectly good parts or worse, missing a failure that's about to happen. The real leap, the real game changer in efficiency, comes from condition-based predictive maintenance, using data to intervene at the exact right time. This is how world-class organizations operate.
Let me leave you with one of the most important lessons I've ever learned out in the field. When a bearing fails, the most common knee-jerk reaction is to assume it was undersized. The temptation is just to go grab a bigger, beefier bearing and slap it in there. But that almost never solves the problem. Why? Because the original bearing probably didn't fail from a lack of capacity. It failed from contamination or misalignment or because it was starved of lubrication. If you only treat the symptom without curing the actual disease, you are guaranteeing a repeat failure.
And that really leads to our final question for you to think about. The next time you're standing over a failed bearing, what are you going to do? Are you just going to replace the part and solve the immediate problem for today? Or are you going to use what we've talked about to dig in, find the root cause, and prevent that failure from ever happening again? That choice right there is the difference between just doing maintenance and actually creating reliability.